you have Biot-Savart's law. Biot-Savart's law basically says that, see, Biot-Savart's law says that the magnitude of magnetic field is directly proportional to the current. It is directly proportional to the current element. Like if this is your current running wire, here is a small portion that is taken. This is known as current element. Suppose here is the point P, and it is directly proportional to sine theta. Sine theta is, if this is position vector, then theta is the angle between the current element and the position vector. And it is inversely proportional to r square, that is the position vector. So when you combine, dB will directly be proportional to I dl sine theta by r square. So obviously you will add a constant k, that is I dl sine theta by r square. Now see, in electrostatics, the value of k was 1 over 4 pi epsilon naught. Here value of k is mu naught by 4 pi. Fine, here the value of k is mu naught by 4 pi. So magnetic field is equal to mu naught by 4 pi I dl sine theta by r square. This is the value of magnetic. So this is what is meant by Biot-Savart's law. All right, right hand thumb rules we have seen. Then application of Biot-Savart's law is very important. So for infinitely, class, you have to remember all these values. So for infinitely long wire, magnetic field will be mu naught I by 2 pi r. Right, value of magnetic field is mu naught I by 2 pi r. And for a semi-infinite wire, semi-infinite means one point is lying at one end and the other end of the wire is stretching up till infinity. So value that time becomes half mu naught I by 4 pi r. So infinite, semi-infinite, then you have circular arc. So see, for circular, any random circular arc, the value is mu naught I alpha by 4 pi r. What is this alpha? This alpha is the angle that is subtended at the center. If it's a circle, proper circular arc, then value is mu naught I by 2r. And if it's a semicircle, value is mu naught I by 4r. And if it's random angle at an angle which is mentioned, that will be this, mu naught I alpha by 4 pi r. These will be the formula that will be used. Fine. Then for circular axis question, this is for the axis. If the point is lying on the axis, if the point is lying on the axis, so mu naught I r square by 2, r square plus x square to the power 3 by 2. This is the formula for it. Let us practice some questions then from this topic. Note down some questions I'm writing. Then try it by yourself. I'll give you 2 to 3 minutes. Try it by yourself, then we'll discuss it. Those who will get their answers, please submit it to me. Yes, any answers? See, it says that a long straight wire carrying a current of 30 ampere is placed in an external uniform magnetic field 4 into 10 to the power minus 4 Tesla parallel to the current. Find the magnitude of the resultant magnetic field at 0.2 centimeters away from the wire. See, current is 30 amperes. Radius is given as 2 centimeters. So we'll write this as 2 into 10 to the power minus 2 meters. So magnetic field for a straight wire, long straight wire, it is mu naught I by 2 pi r. So same thing we'll write mu naught I by 2 pi r. Mu naught is written as 4 pi into, yes, Kulsum, correct answer. 4 pi into 10 to the power minus 7. Current is 30. 2 pi, radius is 2 into 10 to the power minus 2. So 2 pi will give you this 2. Here this 2 will get cancelled. It will be 3 into 10 to the power minus 4 Tesla. So see, this field will act perpendicular to external field, which is given as 4 into 10 to the power minus 2. So if both are acting perpendicularly, so see, net field will be under root b1 square plus b2 square. So that will make it under root 3 into 10 to the power minus 4 whole square plus 4 into 10 to the power minus 4 whole square. That becomes a Pythagorean triplet. So we can directly write 5 into 10 to the power minus 4 Tesla will be the answer. Note it down. Some more questions we'll discuss then. See here, it says that two axial circular loops L1 and L2 of radii 2 centimeters and 3 centimeter and 4 centimeters. These are placed as shown. What should be the magnitude and direction of current in the loop L2? Direction of the current is also asked. So that net magnetic field at point O is 0. See, if net magnetic field is 0, it means both the magnetic fields on the either side of the point O are cancelling each other. And this is actually on the axis. This is like, we can, if I draw it in this manner. This was XY plane, this is YZ plane. So this is actually in YZ plane. So these are points lying on the axis. And both the magnetic fields will be equal because sum of both will be 0. So B1, you can write it equal to B2. So for circular coil where point is lying on the axis of it, that also we had seen. Now see, magnitude of magnetic field due to current I1, it will be mu naught I1. So radius will be 0.03 whole square by 2 into 0.03 whole square plus 0.04 whole square to the power 3 by 2. This will be equal to, see, mu naught I2 and 0.04 whole square by 2 into, again, the same thing, 0.3 whole square plus 0.04 whole square to the power 3 by 2. So this cancels, 2 gets cancelled, mu naught is cancelled. So finally I2 will be equal to 0.03 whole square by 0.04 whole square times I1. And I1 is given as 1 ampere, so that is 9 by 16 or 0.56 amperes. This is right. Write down the solution, then I'll discuss some other topic. Ampere's circuital law says that line integral of magnetic field, means integration of magnetic field and dl, current element that is present. So line integral of magnetic field is mu naught times the current that is enclosed. Mu naught times the current that is enclosed. Fine. So this is Ampere's circuital law. According to Ampere's circuital law, line integral of magnetic field along a closed loop is mu naught times the total current enclosed by the loop. Ampere's circuital law is very important. This Ampere's circuital law can directly be asked in your exam. Questions will also be there. Not only the questions, the law statement part can also be asked. So Amperian loop, there are certain conditions that you have to choose an Amperian loop. We have taken here radiuses are. So by this, you will be having different condition, different cases. If it's for a cylindrical wire C class, this question that we did in the class, all of you have this in your notes, and those even who have not attended the classes that time, I have shared the link already. So this question is very important. Not just it will come as a separate question, it can come as a derivation also. Magnetic field of a cylindrical wire for a point lying inside or for a point lying outside. So if it is a point lying inside, then the value of C, you can even directly remember the formula. So for a point lying inside, it will be mu naught I small r by 2 pi a square. And if it is outside, then it will be mu naught I by 2 pi r. So how it is, if you plot a graph among this, this will be the graph. B is equal to C from the center towards the surface, means throughout inside it is directly proportional to R. So a straight line graph will be obtained. And when you reach the surface and outside you're moving, it will be inversely proportional. That's why we get a hyperbola. So class C, you will get this question, this graph, this part, these also can come from your theory point. It is not necessary that it can come as a numerical. It will normally be asked. Now see, for a solenoid, you have the formula B is equal to mu naught Ni, where N is capital N by length, number of turns per unit length for solenoid. And if it is toroid, formula will be same mu naught Ni, but N's value will be number of turns per the circumference of it, 2 pi capital R. I'm writing down the question. Or practice this question only. Just a second. Start with this question, class. Send me the solution for this question, then one more question we'll discuss. See, this is a very easy question, question 2. Quickly send me the answers. Okay, pa. If they are not, the timings are not suiting you, then it's fine. No need. Hanifa has answered yes, Hanifa, almost. The answer is correct, almost. And what about Kulsum? I think Kulsum, I had also asked you also to shift another batch. Were the timings suitable for you? If the timings are suitable, then you can also shift your batch. If the timings aren't, then it's fine to stay here. Yes, let's discuss this. So Hanifa has answered. Okay, Kulsum. So number of turns per unit length first, let us find out. So number of turns are 500 turns per unit length, 0.5. That makes it 2000. Sorry, 1000. This is 1000. 1000 turns. So B is equal to mu naught N I. I will be equal to B divided by mu naught N. So I will be, B is 2.52 into 10 to the power minus 3. Mu naught is 4 pi, 3.14 into 10 to the power minus 7. N is 10 to the power 3. So when you'll solve this, you will get your answer around 2 amperes. 1.7, yes, it will be around 1.77. So around 2 amperes you will get. Note down those who haven't tried, and others try this question. See, it says that copper wire having resistance of 0.01 ohm per meter is used to wind a 400 turn solenoid of radius 1 centimeter and length 20 centimeters. You have to find out the EMF which produces magnetic field. So see, length of wire use if you calculate. See class, length of wire used. So nobody sent me any answer for this question. Last question everyone did, but this question you did. Length of the wire used will be what? 2 pi r multiplied by the number of turns. That is how we calculate the length. So it will be 2 pi. Radius will be, how much is the radius? 1 centimeter. So 10 to the power minus 2 meters. And number of turns 400. So, and resistance per unit length. Resistance per unit length is given as 0.01 ohm per meter. So total resistance of wire will be, see for 1 meter, this is the resistance. So for the total length of wire is this part. So total length, total resistance, total resistance will be 2 pi into 10 to the power minus 2 into 400 into 0.01. This is total resistance. That will be equal to 8 pi into 10 to the power minus 2 ohms. Now number of turns per unit length. Number of turns per unit length. See, number of turns per unit length will be what? Total number of turns, you know, for this entire length, you know. So for 1 unit length, you just divide it, 400 divided by this term, 20 into 10 to the power minus 2, the entire length. That makes it 2000 per meter. Now, B is equal to mu naught Ni. Current is equal to EMF by resistance. Put this value here. So that will make it B is equal to mu naught N E by R. From here, just find out the value of E as B into R by mu naught N. Everything we have calculated, this is value of N, R radius, you know, N, you know, mu naught, you know. How much answer you got, Hamza? 1 volt. Yes, Hamza. Correct answer. Good. This will be 1 volt when you solve it. Note it down, then we'll practice some other questions. See, for magnetic Lorentz force, you just have to remember this formula. F is equal to QV cross B, QVB sine theta. Rest of the things you'll be able to manage once you know the formula for it. QV cross B is important, or you just remember QVB sine theta. And then secondly, which is important in this, is this part. Lorentz force, when it is asking you just the magnetic force, then QV cross B is fine. And when the question is demanding electric force, then Q into E is fine. But when net force you are writing, then you will combine electric field and magnetic field. That is QE plus QV cross B. So F net will be QE plus V cross B. This formula is also used most of the time. Fine. This is one formula for Lorentz force, and then you have forces between two parallel wires. So this formula also you have to remember in addition to all these. Force between two current carrying wires, and class, this derivation is also asked in the examination. So mu naught I1 I2 L divided by 2 pi d. This is the total force. If you divide the length, bring the length in the denominator of force, that makes it force per unit length. So formula will still be mu naught I1 I2 by 2 pi d. This will be force per unit length. Then the definition of 1 ampere, this can also be asked. And yes, class, this part. Magnetic dipole is A into I, current multiplied by the area of the coil. Now, if n number of turns are there, you will make it as Ni. Fine, let us practice some questions. And if you get the answers, then do reply me in the chat box so that we can discuss it. See, a straight wire of mass 200 gram and length 1.5 meter carries a current of 2 amperes. It is suspended in mid-air by uniform horizontal magnetic field. What is magnitude and direction of the magnetic field? It is like this is suspended in air. This is suspended in air. This rod. So downwards gravitational force will be applied. Upwards the force on the conductor, that is magnetic force, will be applied. So magnetic force will be equal to this mg. That is BIL will balance this mg. Magnetic field will be mg divided by I into L. Mass is 200 into 10 to the power minus 3 kgs. Acceleration due to gravity is 9.8 meter per second. Current is 2, length is 1.5. When you solve this, answer should be around 0.65 Tesla. Check and see. Yes, class. Now torque. So formula of torque is NAIB. N is number of turns of the coil, A is the area of the coil, I is the current, and B is the magnetic field. Class, this derivation can directly be asked to you. NAIB and A into I is magnetic moment. So MB sine theta can also be asked. The way in electrostatics, torque's formula was P cross E sine theta, PE sine theta, or P cross E. Here also torque is M cross B, MB sine theta. This is torque formula. So questions will be there on torque. Simple questions will be there. I have some questions. Let me just display it first. Wait a minute. The answer to this, a rectangular coil of 100 turns has length 5 centimeter and width is 4 centimeters. It is placed with its plane parallel to uniform magnetic field and a current of 2 amperes is passed through the coil. So if the torque acting on the coil is 0.2 Newton meter, then you have to find out magnitude of magnetic field. So see, torque is equal to NBAI sine theta. So magnetic field will be torque divided by NAI sine theta. So torque is 0.2 divided by number of turns 100, area of cross section. See, it's a rectangle. So rectangles will be 2 into L. It will be L into B area when we write. So that will make it 2 into 0.05 into 0.04. That is the area of it. Current is how much? 2 amperes. And sine theta, sine 90 is 1 only. So that I'm writing it as 1. So when you solve this, you should get the answer as 0.5 Tesla. Note it down, and those who have completed, try this question. The same calculations are there. It's just that this is a circular coil given. This is just the difference that is arising. See, circular coil of radius is given, turn, number of turns, current, magnetic field, and theta is not 90. Theta is here is 30. So when you calculate torque, torque's formula will still be NAIB sine theta. So torque will be, number of turns will be 500, area will be pi r square 0.02 whole square. And current is 1 amperes, magnetic field is 0.4, and sine theta will be sine 30 degree. So 500 pi into 0.02 whole square into 0.4 by 2 half. So torque will be 0.13 Newton meter. This will be the answer. Quickly note it down. Last topic is conversion of galvanometer into ammeter and voltmeter. Before that, you have moving coil galvanometer. So from this topic, the principle, the meaning of the device, the construction part can be asked to you. Our principle is directly based on the torque. And construction also, you know, between two permanent bar magnets which have their concave, which have concavities, have radially directed magnetic field along with a spring connected on the soft iron core which connects a pointer. And when the spring moves, it allows the pointer to move on the scale, right? So this is the construction part of it. And this is main important: deflecting torque is equal to restoring torque. Means whatever torque is generated now when the spring is rotating, that is exactly equal to the restoring torque, that is bringing it back to its original position. So deflecting torque is the torque that we have been studying till now, NAIB arc, from the derivation of R cross F. But restoring torque is from your waves and oscillations. So that is K theta. K is the spring factor constant and theta is the displacement, angular displacement. Linear displacement is F is equal to minus Kx, and angular displacement is minus K theta. So from here, deflection is written as NAIB by K, number of turns by area of coil into current into magnetic field by the torsion constant. Now there are two types of sensitivities: voltage sensitivity and current sensitivity, depending upon the definition. So deflection per unit current is known as current sensitivity. Whatever current you have obtained, whatever sensitivity you have obtained, deflection divided by the current, that gives you current sensitivity. And same way is with voltage sensitivity. Get the deflection divided by the voltage. So whatever value of Is you will get, you can describe it by Vs. So deflection per unit current, current sensitivity, and deflection per unit potential difference, voltage sensitivity. Now for the conversion of galvanometer into ammeter, connect a low resistance resistor in parallel to the galvanometer. This we call it as the shunt. So two things you have to remember to convert a galvanometer into an ammeter. Firstly, it should be parallel. Secondly, it should have low value of resistance. Parallel and low value of resistance. This you should remember. Yes, class. So formula of shunt will be Ig into capital G divided by I minus Ig. And conversion of galvanometer into voltmeter, you have to connect two things. One, remember here when you connect the resistor, it should be in series, and the other point that it should be have high resistance. So high resistance series should be connected. And now when you write down the formula for this, formula of the resistance is V by Ig minus capital G. So V by Ig minus capital G is the formula of resistance. So high series resistance. All right. So this is all about magnetic effects of electric current, moving charges, and magnetism. Let us quickly see magnetism as well. Magnetism and matter. Very small topic is there. Firstly, four properties are there for a bar magnet. Attractive property means north and south pole attract each other. Then first property is the attractive property, second property is the directive property. In directive property means if you are allowing a freely bar magnet present, then it will always align itself in north-south direction. Third property is that the monopoles do not exist, means even if you cut a magnet, both the ends should receive one pole. One end should receive north pole, other end should receive south pole. But this is not the case. Other polarity develop immediately. So this is, yes, this is magnetic induction. Magnetic induction means it can induce other substances also. Like iron ball can be induced. It will exhibit magnetic properties. So 4 points of properties are there. Whenever you are asked to write about magnetic field, you can, when you are about to write about bar magnet, you can mention all these points. Then you have certain terms relating to bar magnet. Polarity, you all know, north-south. Then you have magnetic axis, line that joins north and south pole. Just remember, line that joins north and south pole. And equator is the line perpendicular to this magnetic axis. Magnetic length is the complete separation between north and south pole. Means separation, you can say, or you can say length of the magnet. So from this comparison between electrostatics and magnetostatics, we'll analyze the conversion of both of it, and it will be a revision kind of thing also. So for electrostatics, electric charges plus Q minus Q, both the charges are present having the SI unit coulomb. Then you have magnetic charge. Magnetic charge means magnetic strength. Plus M and minus M is used to represent it. It is used to show magnetic strength. When I say magnetic charge means you can use the term magnetic strength. Then dipole you have. For dipole, positive and negative charges are present by a small separation. So electric dipole is given by product of magnitude of any of the charge by its separation. And second is magnetic dipole. Magnetic dipole means plus M and minus M will be there. Magnetic charges will be there. See, in dipole you have same magnitude but opposite direction with a small separation. So here this will also be small separation. Electric dipole is, this was the dipole we had discussed. Axial field of the dipole. See, axial field of the dipole's formula, electric field's formula is 2 kp by r cube. So directly use 2 kp by r cube, no need to use the other formula if it is not mentioned, or something information is not relatedly given to it. Otherwise, directly use 2 kp by r cube. Here it will become in magnetics, it will become mu naught by 2m by 4 pi r cube. For equatorial, it will become minus kp by r cube. Magnetostatics, it will become minus km by r cube. Then again, we have torque as P cross C. Here we have in magnetics torque as M cross P. So PE can be written, it can be expanded as PE cos theta, PE sin theta. This MB also can be written as MB sin theta. Work done is mentioned, work done. This is just a comparison part class. The rest of the things you can also write it by yourself, any part that you find it missing. Now work done is minus PE cos theta. Means minus PE cos theta 2 minus cos theta 1. And all this work done gets stored in the form of potential energy. Here work done, this is also minus m dot b. Wherever you are having electric dipole, the analog of electric dipole will become magnetic dipole. And electric field will become magnetic field. So minus p dot e, here it will become minus m dot p. Minus PE cos theta 2 minus cos theta 1 minus MB cos theta 2 minus cos theta 1. Like this. Then these were the questions. Some terms that are used to describe magnetism. So magnetizing field, the first and very important point. So magnetic field, which is present in vacuum, like for solenoid, you have magnetic field, all these magnetic field. These are known as magnetizing field. Then magnetic induction we discussed. In magnetic induction, total number of magnetic field lines of force crossing per unit area normally is called magnetic induction. Total number of field lines which are crossing a cross-sectional area. Then you have magnetic field intensity. Same thing, it's like you are dividing magnetic field by magnetic field intensity. Then one term was magnetic field intensity. Here you have intensity of magnetization. It means whatever magnetic moment you are getting divided by the volume, per unit volume. So magnetization pole strength is given by this. Then magnetic permeability was mu, which is magnetic induction divided by magnetic intensity. So please class, have a look when you are revising because many things get missed in the revision. So relative permeability is mu is equal to mu r. Mu r is equal to mu divided by mu naught. Where one mu, where without any naught, it is your mu for any medium and mu naught becomes for air. Then magnetic susceptibility is there. Magnetic susceptibility is the symbol chi. And this is equal to intensity of magnetization divided by magnetic field intensity. So now from here, this formula you can easily quickly make the difference between relative permeability and magnetic susceptibility when you see this formula. Now, this relation is also important class. This relation is also asked. Fine. And then differences between, see differences between all these substances. Firstly, you will write about effect of magnets. Like for diamagnetic substances, they are weakly repelled by magnets. Then for paramagnetic, they are feebly attracted by magnets. And ferromagnetic, they are very strongly attracted by magnets. So that will be the first point of difference. Individually also it can be asked, and in difference part also it will be asked. Now in external magnetic field, any magnetization in the opposite direction of wire towards the magnetic field, that is known as diamagnetic, and which acquire feeble magnetization in the direction of magnetizing field, those are paramagnetic, while those acquire magnetization in the direction of magnetizing field. So diamagnetic, weak magnetization, opposite direction. Paramagnetic, weak magnetization, in the direction. And this will be weak magnetization along in the direction. Fine. Then in a uniform magnetic field, also you have to tell that when a freely suspended magnetic diamagnetic rod aligns itself perpendicular to the field. Same thing with paramagnetic, freely suspended paramagnetic rod aligns itself parallel to the field. Also, you have to write about paramagnetic, that a freely suspended ferromagnetic rod aligns itself parallel to the field. So like this, you have to mention. Then susceptibility ranges also you have to mention apart from all these points, class. So susceptibility points also you have to mention how it is lying between -1 and 0 for diamagnetic, how it is lying for 0 to epsilon between for diamagnetic, and more than 1,000, a very positive large number you have for susceptibility in the paramagnetic, last one, third one. Right, and anything else left from this? Permeability also one thing is left, that permeability will be between 0 and 1, slightly less than 1 for diamagnetic, and it will be more than 1 and 1 for paramagnetic, and for ferromagnetic finally you have mu greater than mu naught. Anything else? Temperature, if it comes, then temperature dependency you have to mention in susceptibility, that has come. Susceptibility is independent of temperature. And when you talk about paramagnetic substances, it becomes directly proportional to it. Right, so there's a difference between the materials. Every material makes the property different. Any other thing? One thing also, removal of magnetizing field you can also mention, like when magnetization lasts as long as the magnetic field is applied, that is known as the directional, that is known as the diamagnetic substance. And as soon as the magnetizing field is removed, magnetization is lost, those are paramagnetic substance. And while magnetization is retained even after the magnetizing field is removed, these are known as ferromagnetic substances. Fine, class. Then some examples you can remember here also in the class also I mentioned some examples, like for diamagnetic it will be bismuth, copper, lead, sodium chloride. See, copper, lead, silver, gold. For paramagnetic it will be one you have aluminium, then calcium, oxygen, sodium chloride, copper chloride. Sodium chloride should come in diamagnetic though. It should come in diamagnetic. And all the alloys like alnico. Alnico is one alloy made up of aluminium, nickel, and cobalt. So that alloy is also used when you write it about the paramagnetic. So that is all about the revision of magnetism. Do study it well, revise it well. This is a very theoretical chapter, but the fourth chapter is a very conceptual chapter. Accordingly, revise it. Still having doubts, let me know. Many questions we practiced in today's class, but try to respond. Try to solve the questions within the class only. Then only the revisions will help you. Right, so now we'll have the revision class of EMI and AC together. That is on Tuesday now. Okay, class. So thank you so much. You all can leave now.